My name is Remy Kessler, and I am one of Dr. Michael Levy's incoming medical students and a research fellow in the Department of Neurology at Johns Hopkins Hospital. In this video, I will demonstrate the method we developed for quantifying iron deposition on the surface of the brain for patients diagnosed with superficial siderosis. We ran a 2-year clinical trial investigating whether or not Feraprox, also known as deferiprone, reduces the amount of iron deposition. We obtained pre- and post-clinical trial brain MRIs for each patient included in the study and analyzed them accordingly. We also selected a number of demographic and clinical and radiological characteristics for which to collect data for both the pre- and post-Feraprox administration periods, and I'll show a sample Excel sheet to show you how we organize this data. So as you can see here, we collected information on the sequence, the mean, the volume, the echo time, the reaction time, the number of slices, and then the CSF maximums and CSF means, which is something I'll go into in a little while. But as you can also see, we did this for both pre-drug brain MRIs and post-drug brain MRIs. I'll now demonstrate our method using Osirix software. When analyzing the MRI sequence selected, the first slice that I choose to collect data from is the very first slice that shows any brain matter. So this would probably be my first choice as it's a little bit more substantial than this one. So I'll start here. So from this point, I'll take data from every slice of ventral to dorsal until no more brain tissue can be visualized. So the first step is to click on this drop-down menu and then to click on Closed Polygon. So as soon as you do that, you're going to click on the outer rim of the brain tissue that you want, and then you're going to keep clicking as you encircle the area desired. Now, once you reach this point where you're just about to close the polygon, you're going to double click and that'll close it for you. And this table you can just close. So obviously this isn't as precise as we'd like it to be. So we're going to go back to the same drop-down menu and then click on the repulsor tool. So the repulsor tool will either make this polygon more convex or more concave. So we can go like this, make this area a little bit more precise, and then we can go under here and make this more accurate. So that's not bad. So now this is what needs to be done for every single slice in the entire sequence, which is obviously a little bit tedious. So luckily Osirix has another system of doing it so that it can have a general outline on each slice, and then we can go back and make it more accurate. So what we're going to do is we're going to do this exact same process with the closed polygon for a couple of randomly selected slices throughout. So again, this drop-down table, close polygon, encircle the area desired. Again, we're not looking for a precision right now, we're just trying to get a general area so that the software can calculate areas on every slice for us. So we'll go here, keep clicking until you get the area that you want, double click to close, do two more. If this comes up, you can just close it. And that should be good. So now I go back to any slice really, and in order to get some sort of general area on every slice in the MRI, we're going to click on this, and then we're going to go to ROI and ROI volume. So eventually we're going to click on generate missing ROIs, which is going to give us areas on every slice. But the first thing that we need to do is we need to go to ROI rename. So the default menu will generally have this one selected. Make sure that you click all ROIs in this series as opposed to image, otherwise you won't get the right estimate. So as for the name, it doesn't matter what you pick, so I usually pick a numerical value. And then at this point, I'll go back to what I just said earlier, which was go to ROI volume and then click generate missing ROIs. Now, a lot of the times this requires you to do it more than once in order for the program to give you an area on every slice. So we're going to do it once again. Go here, same process, ROI, ROI rename, and call it 2. Then we're going to go to ROI volume, generate missing ROIs, and now we'll have a general area on every single slice. Now, as you can see, the accuracy is not fantastic, so we're now going to have to go back, and we're going to have to use the repulsor tool, which can be found on this drop-down menu, and we're going to have to go through and make these more precise on every slice. Now, obviously this is tedious, but it's the best way that we know how to do it. And generally it'll only take about, 5 minutes per MRI. But this is what needs to be done in order to get the best possible calculation. So essentially we do this for every single slice, and then we're going to get an estimate through the statistical software in this program. But so this is to be done on every one. So I'll just do a couple more as an example. You can take the repulsor, get the desired outline. And then finish it up here. Again, these are just examples of how it should be done, but this needs to be done for every single slice. At this point, assuming that this has been completed for all slices, you will now go to ROI and then ROI volume. Once you get to this tab, you're going to click on Compute Volume. Now, this is the next table and 3D image that should show up. So the vital statistics here are the mean and the volume. So the reason why we decided to collect information on the volume is just to compare between the pre and post drug MRIs, which are often done at different hospitals or different outpatient facilities, just to make sure that the brain volumes were relatively similar between the pre and post drug MRI, just to ensure that the mean value would be something that we could compare. So we then extracted this information and this information into an Excel sheet, and we did the exact same thing for the post-drug MRI. So what I'm now going to show you, though, is how we decided to standardize these values. So we chose the CSF, and more specifically the CSF found within the ventricles, as it's the clearest source of CSF and also the least likely to be contaminated. It had the lightest and longest T2 signal, and so for this part, I found the MRI slices that had the clearest visualization of the ventricles, and then I used the exact same method of the polygons as before, as we did for all the brain tissue, just this time only encircling the ventricles. So I'll show you how I did that. So in my opinion, these would be the 3 slices where we had the best visualization of the ventricles. And we did this for usually 2 or 3 slices so that we could average the values that we got and therefore get a better representation. So again, drop-down menu, close polygon. This doesn't have to be very accurate as long as the ventricles are within the enclosed area. Did it for this one as well. And we'll do it for this one. So once we have that, if you just click on it, you'll get this table right here. And then you'll have mean and standard deviation, sum, min, and max. So the information that we were interested in collecting was the mean and the max for each slice. So we extracted all of this data, and then we averaged the means and we averaged the maximums to get the best value. So this same method can now be used for all the other MRIs to compare pre and post drug iron deposition on brain tissue, and subsequent statistical analysis can then be performed to determine the efficacy of the drug. This is the conclusion of the OSIRIX tutorial on quantifying hemosiderin deposition. Thank you.